All right, I'm going to start this one in your little conundrum, something, a little puzzle that probably you haven't thought of before, but I want you to think about for a minute. It has to do with satellites. So I don't know if you have satellites on the top of your apartment building of your house, and maybe you've been around when someone came and installed new satellite dishes to look at your satellites, and they go out and on the top of your building or out on your terrace, they put this satellite dish and it's going to point at satellite. They set it up and you get it just pointed just right. Maybe you have to test it and adjust the angle, and then, oh, yeah, they got the signal, and now you got the satellite dish pointed up there. And so you've all, whether you've had that experience yourself or not, you definitely know that, you're driving around, you look around, you see satellite dishes on rooftops of buildings, and they're pointed a certain direction. Okay, now I want you to think about something else for a second. Satellites. So satellites are going around the Earth, and they have to orbit around the very center of the Earth. And then they go around the Earth, and they take time to go around the Earth. And as they're orbiting the Earth, right, they're over different places on Earth all the time. And you can have satellites lots of different heights that have different periods. So the ones that are closer to the surface of the Earth, like the spy satellites, they're really close, or the weather satellites, they orbit very quickly, and they can orbit like in 90 minutes, they can orbit the whole Earth. And satellites that are further away will take longer to go around, but they're going around the Earth, and they keep seeing, they're above different places on Earth. That's why the spy satellites can take pictures, or Google Photos, there's satellites orbiting the Earth, and as the Earth spins and they're going around, they can take pictures of all different places on the Earth and get pictures from all around the Earth for that satellite. But wait a minute, if you are on the Earth and those satellites are going by, maybe you've seen them at night if you go outside and you see, it won't be a plane because it won't have blinking lights, but it'll be a white dot that'll go across the sky very slowly. As it goes across, you can actually see the sun's reflection off of these satellites that are orbiting the Earth as they move along across the sky. But when you put a satellite dish up, you point it at a particular place in the sky, and you don't have to move it. It's not like that satellite dish that you put up is like, okay, I'm aimed at the satellite, and then there it goes, and it comes back around. Oh, there it is. And your satellite dish has to keep like tracking the satellite. The satellite dish points at a given place and never moves again. So it turns out there's some really special satellites that are what we call geostationary, and they have two very important characteristics. The first characteristic is that they have an orbit that takes exactly 24 hours. So they have an orbit that'll take exactly the time of one day. And then the second characteristic is that they'll be straight over the equator, right? And the Earth has a little tilt to it. So this satellite map picture shows a bunch of different satellites. Each white dot is a satellite. And you can see, here, I'll go to the actual page, you can't even see the Earth, because as I touch on every one of these little satellites here, most of the satellites are orbiting really close to the surface of the Earth, and they have orbital periods of, like I said, 90 minutes or so. They're pretty close, or just outside the atmosphere of the Earth, and they make this big white thing here, but each one's actually, a given satellite. So if you click on one, if you go to this website, you can click on any white dot, it'll give you the details about that satellite. And that's pretty cool. And I don't know if you can tell, but there's a ring out here. And this ring that they have out here at a certain distance is how far away it is for, and here you can see it nicely, right? And this tracking map has it so that you can see that if the Earth is spinning and you have a satellite that's over the equator that goes around once a day, then that satellite will be what's called geostationary. You can also have geosynchronous that take 24 hours, but they're not exactly above the equator. That's why you see some that aren't perfect. But the geostationaries are the ones that you can put a satellite dish up and point it, and it'll always be there. So these satellites, you can see how far away they are, roughly. There's a ring of them out there. And they're still actually pretty far away from each other. But these white dots are bigger than the actual satellites. So there's actually a lot of empty space out there still. Same down here. This makes it look like it's all crowded with satellites. In any case, these satellites, since they orbit once a day and have to be above the equator, let's talk about why they had to be above the equator. Let me zoom in a little here so we can see. Let's think about the Earth is spinning and it's going this way. And if one of these satellites was sometimes above, let's say, Cairo, so it was in the northern, and it has to orbit around the center of the Earth, means at some point it'll go into the southern hemisphere. So there'd be no way for a satellite to be over Cairo. Let's say it was over New York, same problem, or London. Any city in the northern hemisphere, if it's orbiting the center of the Earth, if the satellite's above London at some point, it has to orbit the center of the Earth, means at some other point it's going to be over the southern hemisphere as it orbits. So the only satellites that can stay over the exact same city are satellites that are directly above the equator, okay? Because then they can orbit the center of the Earth and go exactly with the spin of the Earth and stay exactly in the same place relative to the surface of the Earth as they take 24 hours to go around. And since they take 24 hours, that means their radius is established by Kepler's third law. You know, the r squared is proportional to t cubed. Maybe I said that wrong. T squared is proportional to r cubed. Relationship of Kepler's law tells us that that is a given radius that must exist for a given period. So we can figure out what that radius of the orbit is from the center of the Earth out to wherever this radius is for these satellites that take 24 hours to go around the Earth. And that calculation is one we're about to do. One last thing about that, though, that I wanted to talk about. So here's a picture from our balcony that I just took. And we look west, sort of on our balcony a little bit. Anyway, you can see every one of these dishes is sort of pointed off in the same direction. And that direction is a little bit southwest, all of them. Okay? And that makes sense because Cairo is a little bit east of most of Europe. And a lot of those satellites that are put up are meant to be sort of easy for Europeans to get to. And so they point south. All of these satellites are pointing south, these satellite dishes. And why is that? That's because we're in the northern hemisphere. These satellites are orbiting the equator. So for us to look at them, our satellites have to point south a little bit. They can point east, they can point east or west as they look south-ish. But they definitely have to be south because we are in the northern hemisphere. When I lived in Argentina, I checked because I was teaching this, and you bet all those satellite dishes point north a little bit because they look up at satellites that are orbiting the equator. So that's pretty cool. They also have to have a period of 24 hours. So to figure out how far away these satellites are, we have to think of the previous derivation that we just did and the previous this is just the Wikipedia answer. We're going to do the calculations here. We set up the same thing we did for this proof, where we set FC, which is Fnet, equal to Fg, which is universal gravitational equation. Make this a little bigger and make it disappear. Good job, Miller. There we go. So you can see that this force of gravity equation is set to the centripetal force equation. The little m cancel. The mass of the satellite does not matter. It can be big or small. The satellite itself does not matter. This m is the mass of the Earth this time because we're orbiting the Earth. This r is what we're solving for. This is the radius of the Earth. This is the radius of the orbit from the center of the Earth. That's that r there. This g is gravitational constant, and this is the speed of those satellites. But we're going to substitute in 2 pi r. We did this exact proof before. And then we get 4 pi r cubed. This time we're solving, we cross multiply. And this time we're solving for r cubed. So we get r cubed. We get this is easy to get because you have the GMT squared, and then the 4 pi squared comes down to the other side. Watch the other screencast if you haven't already done this because we did something very similar to this already. To get r, when we have r cubed, we take the cubed root. So this is a cubed root of these constants. At this point, it's plug and chug if we knew t. And t is 24 hours, but it has to be in seconds. So we need to multiply by 3,600 seconds per hour times 24, and that whole thing needs to be squared. times the mass of the Earth times G. And in the bottom, make sure you put enough parentheses, and you should get the radius of the orbit here to be about 4.2 times 10 to the 7th meters. Now, be careful. That's from the center of the Earth out to here. Center of the Earth out to here. The question asks for the height, which is from the edge of the Earth out to here. So what we need to do is subtract the radius of the Earth from our answer. So if we go back to where we were, we have this number. We're going to subtract the radius of the Earth, which I must have given in the question. Yes, I did. Radius of the Earth, you're going to subtract that. That's 6. And so it looks like that's why this number turns into this number. It's like 42 minus 6 gives you about 36. Yeah, that makes sense roughly. And so this is the height above the surface of the Earth, these special satellites that are geostationary, or what we sometimes call geosynchronous. So the real math here wasn't that tough. You're going to use this same setup that you did before from the previous DDD, but now you're going to plug in for T and solve for R, which requires you to do a cubed root. But it's not that tricky, actually. I find students, the biggest problem when we're doing this in class, and you can see this picture was taken in class. There's my shadow and the reflection and glare. Anyway, that was the most common mistake, is not using enough parentheses, not plugging things into their calculator correctly, and getting it wrong from just plug and chug. So please do this yourself. Don't just say, oh yeah, I get it now. But actually plug all this in your calculator and check your parentheses over until you finally get this correct answer. And that's what we know from looking at this. We've verified that we're confident that we have the right answer here. So this is the actual orbital radius, and this is the height above the surface. That's why this one is called H, because we've subtracted the radius of the Earth for that one. And next time you're driving around, look for those satellite dishes and notice that they're all pointing south. And hope that was interesting enough for you, and that you had a little learning happening, even though you're on this COVID-19 e-learning business. You'll notice some are pointing a little different, even though they're all pointing mostly south or a little southwest. There's little differences because there are more than one satellite that they might actually be looking at, but at least the satellite dish itself doesn't need to change where it's pointing all the time, because those satellites stay in sync with the Earth's spin over the equator. Geostationary satellites, and pretty cool stuff. Any case, I hope you understood that, and I'll see you soon. Thanks a lot.